So, hello Level 2 Chemistry and welcome back to Quantitative Analysis, this time working on Part B, which involves stoichiometry. Okay, so in this lesson we're going to be able to calculate the stoichiometry using the power of the mole, in particular percentage composition, empirical and molecular formulae, and the mole ratio. And these kind of calculations are what Part B, or the written part, or the written test part of your internal will be related about. So I'm going to go now in detail with these three different sections. So the first one is calculating the percentage composition of a compound. So first thing is work out the molar mass of these compounds. Okay, so the molar mass of water and the molar mass of carbon dioxide. Okay. This is the total mass of the compound. In the case of water, it will be 18 grams per mole. In the case of carbon dioxide, it will be 12 plus 32, which is 48 grams per mole. In the percentage composition calculation, you are giving what percentage of the total mass is made up by the elements which make it up. Okay, so for example, what percentage of oxygen is in water and carbon dioxide? So for the percentage calculation, the equation you're using is essentially the mass of the element times 100 divided by the total mass of the compound. So in the case of water, the percentage amount of oxygen in water is 16 times 100 divided by 18, which gives 88.9%, which is essentially saying that 88.9% of the molar mass of water is related to oxygen, or is oxygen. Whereas in the case of carbon dioxide, it will be 32 times 100 divided by 44, which is 72.7%. So as a percentage of the molar mass, there is more oxygen, percentage of oxygen in water than there is in carbon dioxide. Okay, moving on. So here is a series of equations. I want you to pause the video now and then play the video once you have some answers, and we're going to work through this in class in the next few days. Okay, so percentage composition is the first kind of equation that you're going to need to use in Part B, the written test. The second type is to be able to determine the empirical formula and then the molecular formula, given that you're given a certain ratio of elements. Okay, and the memory jog I use for this is purple monkeys drink rum, PMDR. So the first thing you have to do, if you're given percentages of a series of atoms in a molecule, is that you start with these percentages and assume that the total mass is 100 grams, so the mass of each element is essentially the percentage given. So for example, for carbon dioxide, it's 44%, so that means that for 100 grams of carbon dioxide, you're going to have 44 grams of oxygen. Okay, so the second thing is then you convert the mass of each element to the moles using the molar mass from the periodic table. You will have your periodic table with you in the internal, so don't fret about that. But you need to remember that you're using the equation N equals little m over big M, which is the number of moles, equals the mass, which you have calculated in step 1 in grams, divided by the molar mass in grams per mole. That's the second step. So now you have a series of number of moles of each individual element in your proposed formula. Third step is to divide by the smallest. So you divide each value by the smallest number of moles calculated. Okay, so I'm going to give you some worked examples, so don't fret if you don't understand this. We're going to work through this in class. The fourth one is to round the nearest whole number. So this is the mole ratio of the elements and is represented by the subscripts in the empirical formula. So for example, if one element ratio is 1.5, then you have to multiply each element in the problem by 2 to get, of course, 3. And if the element ratio is 1.25, then you're multiplying by 4 to get 5. So it's 1.25 times 4 gives 5. So this is your empirical formula. That's the first step. The next step is to move on to finding the molecular formula from the empirical formula. But first, let's try and calculate an empirical formula. Here's an example. Calculate the empirical formula of a compound which has a percentage composition of 52.2% carbon, 13.0% hydrogen, and 34.8% oxygen. So we're going to break down the steps. Remember that purple monkeys drink rum. So the first thing is we're going to convert percent to grams. So carbon equals 52.2 grams, because we're saying that of 100 grams, 52.2 grams is going to be in carbon, hydrogen is going to be 13 grams, and oxygen is going to be 34.8 grams. That's the first step. Okay, that's your purple part. Okay, so then we have the monkey part, the moles. Number of moles of carbon equals 52.2 divided by 12, which equals 4.35. Okay, so how do we get 4.35? Well, we have the number of grams, 52.2, and we divide it by the molar mass of carbon, which gives you 4.35 moles of carbon. We do the corresponding calculation for the other individual elements in the molecule. So for hydrogen, you'll have 13 moles. For oxygen, we'll have 2.175 moles. Okay, that's the monkey part, moles. The third part is drunk, so it's divide by the smallest. So the smallest number, as you can see, is 2.175, number of moles of oxygen. So we simply divide each of the other moles by that number. So for carbon, we have 4.35 divided by 2.175, so that gives you the number 2. Hold on to that idea. Hydrogen is going to be 13 divided by 2.175, the smallest number, which gives 5.98, and oxygen is going to divide by itself, which is going to give you 1. So therefore, the empirical formula, when we round, is going to be C2H6O, because the numbers we get in step 3 is essentially the subscript for each individual element. So I hope that's clear. So that's the empirical formula. The next thing we have to do is move from empirical formula to the molecular formula. Okay, so for this we have M divided by E. So you divide the actual molar mass of the compound, which you'll be given in the question, so this is kind of a merit question because you've got the 2 steps, by the molar mass in the empirical formula. Okay, and you multiply by E, and this is the number you get when you multiply the empirical formula by this number. Okay, so using the previous example, in the question you're told that the molar mass of the compound, which you don't know yet, is 92 grams per mole. So you use your answer in part A to determine the molecular formula. So the empirical mass you can calculate by adding up all the constituent atoms in your empirical formula. Okay, so you've got 2 carbons, so you multiply 12 by 2. You have 6 hydrogens, so you multiply 1 by 6, and you have 1 oxygen, which is 16. So the molar mass of the empirical formula is 46 grams per mole. You're told in the question it's 92 grams per mole for the actual compound, so that means that you have to multiply the empirical formula by 2 to get the actual molecular formula. So the empirical formula is C2H6O, so all you're doing is multiplying each of those individual atoms by the coefficient you've calculated in the last step, which is 2. So C2 becomes C4, H6 becomes H12, and oxygen becomes O2, because you have 1 times 2 becomes 2. So the molecular formula from the empirical formula you've just been given is C4H12O2. Okay, so here's a couple of examples, 1A and 1B, of trying to understand the ideas between empirical and molecular formula calculations. So because you're doing up to 3 steps in this calculation, this is an excellence level question. So if you want to get excellence, you have to understand how to do this. So here are 2 examples. I want you to pause the video now, work through the examples on a piece of paper, and come to class with your answers so we can have a look to see if you're on the right track. So pause the video now. Okay, so here are 2 other examples that you can work through again to make sure you're on the right track. Same again, write down the answers showing all your working, pause the video, work through these examples, and then we're going to go through them in class together. And a final example of empirical molecular formula calculations using the cysteine molecule. Again, same idea. Pause the video, work through the problems, and then we can go through them in class. Right, so the final example is mole ratio calculations, kind of the key advantage of stoichiometry and why we have the mole. So these are simply determined by looking at a balanced equation. The number for any reactants is considered the number of moles. So for example, in the equation of sodium hydroxide reaction with sulfuric acid, giving sodium sulfate and water, 2 moles of sodium hydroxide react with 1 mole of sulfuric acid to give 1 mole of sodium sulfate and 2 moles of water. So therefore, the mole ratio between the sodium hydroxide and the sulfuric acid is 2 to 1. Which essentially means in a reaction between these two chemicals, you need twice the number of moles of sodium hydroxide to react with 1 mole of sulfuric acid. Okay, so to get the ratio from the equation of unknown over known moles, U divided by K, you times the given number of moles in by this ratio. So here's an example, a couple of examples or questions here, 1, 2, 3. I want you to pause the video now to see if you can work out the number of moles of the unknown reagent. And we're going to go through this in class. Okay. And we can also do word equations. So an example question here, which we're going to work through now, is what is the mass of water that is produced in the complete combustion of 25.4 grams of methanol according to the following reaction, where 2 moles of methanol react with 3 moles of oxygen to give 2 moles of CO2 plus 4 moles of water. Okay, so the first thing, just like your titration calculations, is you look at the question and you identify the known and unknown components of the question. So in this particular case, methanol is the known, because we know that there are 25.4 grams of it, and that water is the unknown, as that is the mass we are trying to determine. Okay, this is where our equations come in again. So the first thing we do is we go mass to moles. We convert the number of moles of the known using the equation we have, number of moles equals mass over molar mass. So putting in the numbers, the number of moles of methanol is 25.4 divided by 32, which gives approximately 0.794 mole. Now notice that the answer is in 3 significant figures, so you need to put your answers in 3 significant figures in chemistry in order to get full marks. Okay, so then we have the ratio. The mole times the ratio of unknown to known equals the moles of your unknown. So in this particular case, we want to find out water, so the ratio is going to be the ratio of the known to the unknown, which is going to be 4 divided by 2, which is 2, times the known, which is 0.794. So that means that you have 1.59 moles of the unknown, the water we're trying to find. So now we have a number of moles. We have a molar mass of water, which we know is 18 from the periodic table. So then we go back to moles to mass. So the mass of water is going to be 1.59 moles of the 18 grams per mole, using the equation N, or rearranging the equation N equals little m over big M, to give the answer, which is 28.6 grams of water. Okay, so hopefully that's clear as mud. So here's some example of some ratio calculations I want you to work on in your own time. So pause the video now and try and work out the unknowns of these 4 equations. Once you think you've got the answer, then come to class and I'll have a look at them and see if we're on the right track. Okay, so here's a practice assessment for the internal part B, which I want you to work on now, and then we're going to work on it in class together. So again, just pause the video now and see what answers you start getting. So this is an excellence level question because there's more than 2 steps required. So it's about finding the empirical formula first and then working out the molecular formula from the question. Okay, so that's the extension from the previous slide, because you're now given the idea of another acid being formed. And the final part 3 is again something we're going to work on in class, so pause the video now and work through it. And this is the second practice assessment, which we're going to work through in class. So again, you're finding both the empirical and molecular formula. And that's again an excellence level question. And another 2 questions to practice on. So again, pausing the video and working through it. Okay, so here's just a few last minute tips before you start doing the second part, the part B of your internal, the more written part. Always indicate what you are working out. For example, number of moles of carbon. Okay. Show all the units in your calculations after each number. Obviously, you don't need units for ratios or percentages. Always use 3 significant fingers for your final answer. Okay, so that's right at the end. Before that, you're carrying all the numbers over. And check all your calculation work once again to make sure that your data entry was correct. And there's the answers to the slides previous, so you can check your answers there. Excellent. Okay, so with that in mind, that's part B sorted out. So hopefully you're all on target now for excellence.